We're going to be talking about graphing the rational functions. So a rational function is some function of the form, it says p of x over q of x, where both are polynomials. So we have passively a function on top, a function on bottom. And the little example we see on the graph over here is the kind of most basic, the parent function, 1 over x. And you can see our graph, these blue branches, two different pieces of a graph, are split, that we have two pieces. And the reason we have two pieces is because our denominator is x. And remember, we're never allowed to have our denominator equal 0. So x can't equal 0. And so right here at the line where x would equal 0, we have what's called an asymptote, a vertical asymptote where x is 0. And we're going to see on our different examples that we're on all these rational functions, we're always going to have a vertical asymptote, which kind of cuts the graph into these branches wherever the denominator equals 0. Now, because we have this vertical asymptote, we're also going to have a horizontal asymptote. The horizontal asymptote doesn't have anything to do with the denominator. Instead, the horizontal asymptote has to do with something called the long run behavior. So if we think of the function 1 over x, as we plug in giant values for x, so even just like 1 over 4, 1/4, like that's here on the graph, 1 over 10, it's not on the graph, but like 1/10, if I go 1 over 100, these values, even as 1 over 1,000,000, well, 1 over something big is going to get close to 0. It's never going to be able to hit 0. As I keep going across this way, it's never going to actually cross that axis of 0, but it's going to get closer and closer. And the same thing is happening here as I'm plugging in negative numbers. So if I plug in -4 to my function, 1 over -4, it's negative 0.25. And we're going to get like negative values that are very close to 0 kind of as I come across. And so that is what the horizontal asymptote represents. Okay, so down here, our rational function isn't always going to be 1 over x. It might take some other form. Here we have it. It says y equals a over x minus h plus k. And remember, our h and k typically translate the graph, left and right, up and down. And that's what we're seeing here. But the basic that we need to know is that the vertical asymptote, this up and down asymptote, is always going to occur where the denominator equals 0. So we're going to be looking at that little denominator part. And the horizontal asymptote, if we're in this form, is always going to be the k value, because that's kind of how our graph moves up and down. So that's what we're going to look at on these graphs. So number 1, it says identify the asymptote, state the domain and range, and graph the function. We have g of x equals -2 over x minus 1, and then plus 3. So our first goal is going to be find that vertical asymptote equation. Like I said, we're looking in the denominator. So if our denominator is x minus 1, we want to think what makes that 0, and that's x equals 1. So x equals 1 makes that denominator 0, and so that's where our vertical asymptote will be, at x equals 1. Okay, that also means our domain is going to be all real numbers except x cannot be 1. Because we draw this asymptote in, but really there's going to be no point on our graph where x equals 1. So when we're thinking of our little table over here, we're going to put 1 kind of in the middle, even though it's not a point on our graph, and we're going to choose points above and below 1, or really to the left and to the right of 1. So if 1 is this, x equals 1 is this line, we want to go maybe 0 and -1 to the left, and 2 and 3 to the right. Okay, so all of that information we get because the denominator was x minus 1. Okay, our horizontal asymptote comes from whatever's being added over to the side, because that's like the translation up and down. And so in this one, we get y equals 3. And so again, we can graph that horizontal asymptote on the graph. And then that also tells us our range is all values except where y is 3. So all real numbers except y cannot be 3. And then to find the actual branches to actually plot the points of our graph, we need to use these blue values and plug them in to our function, our g of x function over there. So plug them in for x. My first one is -1, so I'm going to have -2 over -1 minus 1. I'm plugging in that -1 and then plus 3. Okay, so when I do that math, -2 over -2 is +1. 1 plus 3 is 4. So my point is -1 comma 4 on the graph. Then I want to plug in the next value, 0. So -2 over 0 minus 1 plus 3. So again, plugging these x values into my function. So -2 over, it's going to be -1. That's +2 plus 3, we get 5. Okay, and I'm going to go ahead and plot those points. So -1 comma 4, -1 comma +4, and -1 comma 5. 0 comma 5. And those are enough to kind of sketch this graph. Remember, when we're sketching the branch, we never want to cross over either asymptote. So we're going to go through those 2 points, but then we're just going to get close to both that vertical asymptote and the horizontal asymptote, kind of curve it in there. Okay, now we're going to plug in our other values, 2 and 3. So plug in +2. I have this -2 over 1, so that's -2 plus 3. That's going to be +1. And then -2 over 3 minus 1 plus 3. I have -2 over 2, so that's -1 plus 3 is 2. So my last 2 points here, +2 comma 1 is here, and then +3 up 2 is there. So those 2 points are going to help me to form this second branch. Again, curving with the asymptotes through those 2 points. And that is how we graph one of these rational functions. So we're going to find all the parts and then also plot the points. Okay, down here on number 2, we have h of x equals 1 over x plus 4. And again, our starting place is what is that denominator? How can I find my vertical asymptote? So my denominator is x plus 4, and so x cannot be -4. So for my asymptote, I'm going to say x equals -4 because that's the actual line on our graph, vertical line, where x equals -4. But then my domain is all real numbers except x cannot be -4. And then that -4 is also that mid value on our graph, on our plotted points. We're going to choose points to the left and to the right of that value. So if -4 is our line, to the left I can go -5 and -6, and to the right I can go -3 and -2. Then the horizontal asymptote we found by what is being added here at the end. And in this one, we don't have anything. You can think of it as like a +0 because nothing is being added. So our horizontal asymptote is the line y equals 0. And our range is all real numbers except y is not going to be 0. It's going to get closer and closer to 0, but it won't ever hit it. Okay, now we can go ahead and find the points. And so plugging in -6, we have 1 over -6 plus 4. We're just plugging in the -6 to my x value of my equation. And so I get 1 over -2, or -0.5. Okay, if I plug in the -5, 1 over -5 plus 4, I get 1 over -1, which is just -1. And I like to do the first 2, graph it, and then do the second 2. So I'm going to plot these. -6, comma -0.5, and -5, comma -1. See they're a little bit closer to the asymptotes, but we're still going to be using those 2 points to kind of curve along where those asymptotes are. So 2 points and that nice curved part of the graph. Then plug in our other 2 points. So plug in the -3. 1 over -3 plus 4. Well, that's 1 over 1, which is 1. And 1 over -2 plus 4. That's 1 over 2, which is 1/2 or 0.5. Okay? So when I plot these points, I'm going to plot -3, comma, +1, and -2, comma, 0.5. Okay, and then nice curve through those points and next to our asymptotes. Okay, and so those are how you graph rational functions if they are in the form where we don't have any x's on top. So that's kind of what was key here. I don't know if we noticed it, but in both of our examples, we did not have an x in the numerator. We only had an x in the denominator. So this type is x is in the denominator only. Right? On the next page, we're going to see what happens when x is in both the numerator and denominator. So here, x is in the numerator and the denominator. Okay, so this time, instead of looking like 1 over x or 4 over x or something like that, we're going to have something that is x over x. If you see these examples on this page, I have 2x plus 1 over x minus 3. So I have x's in both the numerator and denominator. So when we see our function look like this, we're going to have to change a little bit how we find the horizontal asymptote. Okay, the vertical asymptote is still always wherever the denominator equals 0. It might be an equation like this cx plus d. It could be just x minus 3 like we see down in this first example. The horizontal asymptote, instead of being a plus k, a lot of times we're not going to see a plus k in this, and it's not 0. Instead, we're looking at what is the long run behavior, and it's going to be this a over c. And I'll show it to you in our first example. Okay, so again, find our asymptotes, graph everything here in our first example. Number 3, 2x plus 1 over x minus 3. And I start out by finding the vertical asymptote, which is wherever the denominator equals 0. And so in this case, it's x equals 3. I can plot my asymptote, and then I can also use that to say the domain is all real numbers except where x cannot be 3, because that would make the denominator equal 0. And then our 3 is still going to be like the midpoint of our table. And so I can go to the left, 2 and 1, and to the right, 4 and 5, from that midpoint. For my horizontal asymptote, this is where it changes from the first side of the page, that we're going to look, it says at a over c. A over c is this value over this value. And it's kind of like, what is the coefficient of x on top over what is the coefficient of x on the bottom? And so we have like a 2 over 1, which is just 2. So y equals 2. We're looking always at the coefficient of the x, not the little constant terms, not the 1 and 3 or 1 and minus 3, but the part in front of the x. So that's where we're going to get our horizontal asymptote from if we have x's on top and bottom. Always this a over the c in our equation. Okay, so 2, y equals 2, is our horizontal asymptote. And then that also determines the range is all real numbers except y can't be 2. And the reason it's 2 here is just like when I was plugging in all those values on that first page to say, if I plug in 10, if I plug in 100, if I plug in 1,000, like 1 over 10, 1 over 100, 1 over 1,000, it's getting closer and closer to 0. Well, here, if I plug in really big numbers, if I plug in 100, so I'll have like 2 over 100 plus 1 and 100 minus 3. They're saying basically that's going to be like 200 over 100, which is getting close to the number 2. Now we have this plus 1 and we have this minus 3, so it's going to be slightly off, like 201 over 97, but that's still going to be really close to 2. And if I plug in something bigger, plug in 1,000. So that's 2001 over 1,000 minus 3, which is going to be like 997. And so that is almost 2. It's closer to 2 than the previous one was. So as I get bigger and bigger numbers, my function in the long run is going towards the number 2. So that kind of 200 over 100 is where that it comes from. So just, you don't have to know that, but it's good to know maybe the why and not just listen to me. So we want to actually plot some points to get both of our branches. So this 1, 2, 4, and 5, we're going to plug in to our equation. So I have 2 times 1 plus 1 over 1 minus 3. And so on the top, 2 plus 1 is 3. On the bottom, I get negative 2. So 3 over negative 2 is negative 1.5. Okay. Then I'm going to plug in the 2. So 2 times 2 plus 1 over 2 minus 3. So on the top, 2 times 2 plus 1, I get 5. And on the bottom, I get negative 1. So that's a negative 5. And I'm going to go ahead and plot those points. So positive 1, comma negative 1.5. And positive 2, comma negative 5. So our points here aren't as close to our asymptotes as some of our previous examples, but it is still what we want to do is go close to our asymptotes through those 2 points, staying within like the orange and green lines. You don't want to cross over into any other like quadrant of those lines. You can cross over our actual like axis, the x-axis, the y-axis. You just don't want to cross over the asymptotes. Okay, and continue with our other 2 points. So plug in 4, 2 times 4 plus 1, and 4 minus 3. So I have 9 over 1, which is 9. And then last one, plug in 5. 2 times 5 plus 1, it's 11 over 5 minus 3, which is 2. 11 halves is 5.5. So I'm going to plot those last 2 points. Positive 4, positive 9, and positive 5, and then 5.5. And again, through those 2 points, but also staying within my asymptotes. A nice curve. Okay, and so that is number 3. For number 4, kind of same process. We want to look at the denominator first, always denominator first, to find the vertical asymptote. So what here could x be to make the denominator equal 0? And remember, when we have 2x or 7x, if there's no plus or minus, x being 0 will make the denominator equal 0. So our vertical asymptote is at x equals 0, right there on the axis. Our domain, all real numbers except x cannot be 0. And then we want to put 0 in the mid of our table. For our horizontal asymptote, we're looking at the coefficients of x in the numerator and the denominator. So here, like 4 over 2, which reduces to 2. So y equals 2 is again our horizontal asymptote because it's kind of whatever that reduces to. So y equals 2. And the range is all real numbers except y is not 2. So it's going to be all the values except it cannot cross that asymptote. Okay. For our table, if 0 is our midpoint, 2 points to the left, -1, -2, and 2 points to the right, 1 and 2. I'm going to plug those x values into our equation to get the y values. So plugging in -2, I get 4 times -2 plus 1 over 2 times -2. So it's -8 plus 1 is -7. and 2 times negative 2 is negative 4. So negative 7 over negative 4 is a positive 1.75. Plugging in negative 1, 4 times negative 1 plus 1 over 2 times negative 1. So in the numerator, I get negative 3, denominator negative 2. So negative 3 over negative 2 is a positive 1.5. And let's go ahead and graph those. So negative 2, 1.75. Oh, really close here to that line, but right beneath it, the line is at 2, and then 1.5 is there. So you can see very, very close to the asymptote in this case. So when we're wrapping, it's going to be very close as we draw our branch. But still through those points, 1.75 and 1.5. All right, plugging in positive 1 and positive 2. So for positive 1, I have 4 times 1 plus 1. That's 5 in the numerator over 2 times 1, which is 2. So 5 halves is 2.5. And then our last one, 4 times 2 plus 1, that's 9 over 2 times 2, which is 4. So 9/4 is 2.25. Okay, so these ones are going to be just above our green line, 1 comma 2.5 and 2 comma 2.25. Try and get it in there. Okay, so again, very close to our asymptotes, but still curving along them. Okay, why don't you try number 5, pause the video and come back. All right, so for this last equation, we had 3x over x plus 1. You start with the denominator. What can't be x? So what would make the denominator equal 0? And it's negative 1. So x equals negative 1. We have our line at x equals negative 1, and our domain, all real numbers except x cannot be negative 1. Negative 1 also goes right there in the middle of our table. For our horizontal asymptote, we're looking at 3x over 1x. Again, the coefficient on the top and the coefficient on the bottom. So 3 over 1, so y equals 3 is our horizontal asymptote, and our range then is all real numbers except y cannot be 3. Okay. Plugging in points, I plugged in 2 points to the left of negative 1, negative 2 and negative 3, and 2 points to the right of negative 1, 0 and 1. And we got these values, and we're able to plot them.